Yes, so we now look at the divergence of vector and tensor functions in this second part of my lecture on calculus of scalar vector and tensor functions. So, with this single objective, we move ahead at completing the this set of lectures on the mathematical tools that we will be requiring in this course. So, divergence operation on vectors and tensors. What is this divergence? So, divergence is when we have the del operator operating on a vector with a dot product in between. So, del dot A. Now, you will recall that this kind of an operation is needed to define the local volumetric strain rate in any fluid particle. Remember, it is del dot V. So, V being the vector. So, if you look at this operation on vectors, del dot, so you are now, by now you are familiar of how to proceed. So, I'll do it relatively quickly. So, EI cap del xi 1 over hi is the scaling factor, dot aj ej cap, and then the usual way of working, the calculus operator is first operated on the vector and then the dot product with EI cap is taken. So we get finally a term 1 over hi del aj del xi ei dot ej plus aj ei cap dot del ej cap del xi. This is the most general result that you can get for any arbitrary coordinate system. Now for orthogonal systems, we are already familiar. Ei dot ei cap dot ej cap. This is for orthogonal system, it is equal to delta ij, the Kronecker delta, and already discussed in my lecture 5. And so del dot a becomes this term on the right, and finally the Kronecker delta can be just removed by taking j is equal to I in the first term. So if you take j is equal to I, because it's a summation over I and j as far as the first term is concerned, both are repeating indices, but since Kronecker delta only contributes when j is equal to I, so we can directly simplify by setting j is equal to I the first term. So you notice that aj has been changed to ai in the first term. So 1 over hi del ai del xi, this is the first term, summation over I, because I is the repeating index, and second term is aj ei cap dot del ej cap del xi. We can't simplify this since we are only specifying an orthogonal system. So the second term remains as it is, and of course it has two repeating indices I and j. Now for Cartesian system, we all know that the unit vector derivatives are all 0 and hi is 1. So the divergence in Cartesian system is simply del ai del xi. So that means the components of the vectors along different directions, you take their corresponding partial derivatives with the coordinates along those directions and just add it up, because I is again the repeating index, so the result is a scalar. Okay, on the right we don't see any presence of any unit vector, so we simply say del ai del xi, which is sum del a1 over del x1 plus del a2 del x2 plus del A3, del X3, these three getting summed up. Now to have a look at what happens in cylindrical coordinates. So again we start with the general expression for orthogonal systems. So for orthogonal systems we have these two terms, and as I have written, both I and j have to vary r theta z over r theta and z, and we know there's various scale factors. hr hz is 1 and h theta is r. So the first term, which has only I as the repeating index, will simply expand like this, sum over I, so you get this term. And the second term, notice that since we know, as I've mentioned earlier also, that the partial derivative is only with respect to theta, so we basically fix I as theta and vary the j index. Okay, so I is fixed as theta for the second term. So a r and a theta, these are the two values of j that you need to consider. The third value you don't need to consider because the unit vector del Ez cap doesn't vary with any coordinate. So the two terms will look like this when we will expand the second term over the repeating index j. So as I said earlier, we are also expanding by the repeating index I, but because it only contributes when I is equal to theta, so that's why it's formally not expanded that way, and I is just fixed as theta. All other terms are basically 0. So whatever way you choose to look at it, for me it looks a very straightforward way of handling these repeating indices in cylindrical coordinates. So j is r and theta, and I is theta will contribute only in summation, as I have explained, written in red text. Now to take this further, right, so we look at the second term in the divergence of a vector. So as I pointed out that since I am fixing I with theta and I just need to vary j over r and theta, so I'll get these two terms. The second term being orthogonal set of unit vectors, so e theta cap dot minus er cap, it goes to 0. And the first term is simply ar over r, because e theta cap dot e theta will be 1. So finally we have the divergence of vector in cylindrical coordinates, the sum of first term and the second term. So I have this expression, which is also given you in your second mathematical sheet directly, sheet on mathematical identities, theorems, and results from vector calculus. So we have this. Notice that in this divergence of A in cylindrical coordinates, you not only get the partial derivatives of the components of A, but you also get a term, an algebraic term, AR over R. So this result is a scalar. And now we move to divergence of tensor of rank 2. So the procedure by now is fairly familiar to you. So we write these del and t using their respective representations and indicial notation. So notice that once I use the index I in the del operator, I am using other indices j and k for representing the tensor. So again the dot product is left to be considered later on. First, the partial derivative operator 1 over hi del xi is first considered, and so the del is missing actually there. it's not correctly written. So 1 over hi del xi, and then that is operated over the tensor. So one by one, since it's a quantity comprising of three things, tjk, the components, and the unit vectors ej cap, ek cap involved in the dyadic product. So we one by one, turn by turn, using product rule, we differentiate, and so we get three terms and finally take the dot product. Now remember, in taking the dot product, the order of the various vectors, the way they have been written, is preserved, and this is important in taking involving any operation on dealing with tensors, because you're not allowed to change the order, because that changes the meaning in the term. So you remember this. So del tjk del xi 1 over hi, and ei cap, ej cap involved in the dot product, and ek left as it is, and so you get the three terms in a similar manner. Now for the orthogonal coordinate systems, we already know that this ei dot ej can be written as Kronecker delta, delta ij. So the first and the third terms are having this ei cap dot ej cap dot product, so they are simply simplified for orthogonal coordinate systems by using the Kronecker delta, which eventually can be simply removed by taking j is equal to I. So the last, you can say, the last simplification stage for orthogonal coordinate system has these three terms, del tik del xi 1 over hi ek, and plus tjk ei cap dot del ej cap del xi 1 over hi, and of course ek, plus tik del ek cap del xi 1 over hi. So in the first and the third, you have I and k as the repeating indices, and in the second term you have I, j, k all being treated as repeating indices. So once we have completed the simplification for orthogonal coordinate systems, we move on to seeing the result for our most widely utilized Cartesian system. So del dot t in Cartesian. So the second and third term involve the partial derivatives of unit vectors, so put them to 0. And in the first term, we have to take hi, all the scale factors, as 1. I have not written it here, but it is implied that hi will be taken as 1. So the result is a vector. This is something worth noting, that when you take divergence of a vector, you get a result which is a scalar, indicated on the left, for cylindrical coordinate systems as well as Cartesian on the previous slide. And when you take divergence of a tensor of rank 2, you have a lesser complex quantity which is a vector. So something worth noticing. Again, I and k being repeating indices, so sum over I and k is implied, right? So now when I look at the cylindrical coordinates, I start directly with the second term, and second term is tjk, and again I fix I as theta, because only theta coordinate derivatives of unit vectors are there. So the term looks like this, and so j, as I said, needs to be varied only over r and theta, because z doesn't have any unit vector derivative. So therefore the second term is expanded by summing over j and k. So j is first taken as r, so t r k r e theta cap dot del e r cap del theta e k plus the other value of j, t theta k upon r e theta cap dot del e theta del theta cap, and of course the vector ek cap. We have not yet summed over the repeating index k, so I am just doing it for j first. So you will notice that in the final result I have only a single term, because e theta cap dot minus er cap term, the second term, becomes 0, and so I only have to sum over k now to complete this second term, and k has to be varied over, again as I said, all the three coordinate directions r, theta, z. So we simply have trr er cap plus tr theta e theta cap plus trz ez cap and divided by r. So this is the second term. Now the third term was tik del ek cap upon del ek cap del xi rather, and 1 over hi. So again I can be fixed as theta, and so therefore t theta k del ek cap del theta, of course 1 over r, is the scaling factor in theta direction. So now we can now open up the summation over the repeating index k. So since the derivative is involved, we'll only do it over r and theta. So t theta r by r del er cap del theta plus t theta theta upon r del e theta cap del theta, and so the result t theta theta by r del e theta del theta comes out as minus er, so minus t theta theta r er cap plus, of course the other term is t theta r by r e theta. So if I now combine all the three, the third, second and the first term, so first I have combined the second and third term, of course, and so second and third term comes out as a vector like this and the first term is now taken care of at the end, because it just requires a summation over I and k. So this is how it looks like if you sum over I and k. So the first term expands in this manner, and in the last I have written the final expression of divergence of a tensor of rank 2 by summing all the three, first, second and third. So you have the result before you, and this result is just the outcome, the logical outcome of the various operations that I have taught you to handle in the manner that has been indicated. So it means that now we have gone through all the calculus operations dealing with scalars and vectors and tensors that are normally required in our fluid mechanics subject, and wherever you will be doing any kind of modeling, you will not be going outside the domain of these calculus operations that we have covered in these two lectures. So as I said, the essential idea was that the foundations in the various mathematical tools need to be strong, so that you feel very confident in and not getting not having trouble with the mathematics, dealing with the mathematics in fluid mechanics subject. So the essential idea of these lectures was this only, and as far as the syllabus and the course goes, wherever we will require Cartesian and cylindrical coordinate expressions. So those expressions by and large are available in the second sheet, and you can just handpick them and use them with the confidence that you know from, it's not magic how we are getting those terms. It's a very well-grown mathematical procedure that has led to the various expressions. Okay, so with this I end this second lecture of mine, and there'll be no more such lectures on dealing with the maths only. And so I request you to go through these lectures carefully, listen to them carefully, and I don't foresee any kind of difficulty if you pay attention to the details and aspects involved in these lectures. And also you can do some of the mathematics that I have done in these lectures yourself, and then you will feel fully confident. Okay, thank you very much.